From the moment we take our very first step to watching the stars drift across the night sky, our lives are just completely defined by movement. It's so fundamental to our existence that most of the time we don't even think about it. But what if we could learn to speak its language, to really understand the elegant, simple rules that govern every journey we ever take? And just think about that for a second. It really is everything. It's not just you and me walking around. It's the blood flowing in our veins. It's a leaf falling from a tree. It's the entire earth revolving around the sun. Everything, everywhere, is in a constant state of motion. It's this incredible, shared experience that connects everything in the cosmos. And that's really all it is. At its core, that's the big idea. Now, it sounds almost too simple, right? But describing that change with real precision, well, that's where the beauty and the physics of it all really begins. For this explainer, we're going to keep it simple and focus on the most fundamental kind of movement, motion in a straight line. All right, so let's dive in. The very first question we usually ask about something that's moving is pretty obvious. How fast is it going? We all have a gut feeling for what that means, but to really speak the language of motion, we need a word that's a bit more precise, and that word is velocity. Think about when you're driving. Your speed is never perfectly constant, right? You speed up, you slow down for traffic. The average speed for your whole trip doesn't really tell you how fast you were going at one specific moment. And that's exactly what instantaneous velocity is for. It's the number on your speedometer at the exact instant you glance down at it. So this is where it gets really interesting. I mean, an instant doesn't last for any amount of time. It has zero duration. So how can an object travel any distance in literally no time at all? It kind of sounds like a paradox, doesn't it? But physicists have a really clever way around this. Instead of trying to measure something in zero time, which is impossible, they do something smart. They measure the average velocity over smaller and smaller and smaller windows of time. The whole idea is that as that little time window shrinks and gets closer and closer to zero, the average velocity you calculate will get closer and closer to the true velocity at that single instant. Okay, now look at this table. It shows this zooming in process perfectly. Let's say we want to find the exact velocity at the 4-second mark. Look at that first column. The time interval gets smaller and smaller, from 2 seconds all the way down to just 1/100th of a second. Now watch what happens in the last column. The average velocity starts to settle down, homing in on one single stable number. And there it is, 3.84 meters per second. By zooming in on that moment, we can say with a lot of confidence that this is the real instantaneous velocity right at that 4-second mark. So the trick is, we find the velocity at an instant by looking at what's happening just around that instant. Pretty neat, huh? Oh, and just a quick but really important point here. In everyday life, we use speed and velocity like they're the same thing. But in physics, there's a key difference. Velocity includes direction. Speed is just the number, how fast. Velocity is how fast and which way you're going. And that's why velocity can be negative. It just means you're moving in the opposite direction, like backwards. Okay, so we've got a language for how fast something is going. But what happens when that fast changes? You know this feeling. We all do. It's that pushback into your seat when a car takes off, or that lurch forward when the driver hits the brakes. That feeling, it has a name. It's acceleration. And this is so important to get. A car can be going incredibly fast, but if its velocity is constant, it has zero acceleration. Acceleration is all about the change. You can accelerate by speeding up, sure, but also by slowing down, or even just by changing your direction, like turning a corner. You can think of it in these 3 flavors, which we experience all the time. That feeling of getting pressed into your seat when you step on the gas, that's positive acceleration. That sudden lurch forward when you slam on the brakes, that's negative acceleration. And that smooth, calm feeling when you're just cruising down the highway at a steady speed, that's zero acceleration. You're moving fast, but your velocity isn't changing. So let's go way back to the 17th century. A guy named Galileo figured out something absolutely profound. He realized that for a really common type of motion, any motion with a constant acceleration, there was a kind of secret code, a set of simple equations that could predict the future. And this is that code. This is his toolkit. Now, don't let the letters scare you. These aren't just formulas to memorize. They're powerful relationships. They mean that if you know where something started, how fast it was going, and what its constant acceleration is, you can predict exactly where it will be and how fast it will be going at any moment in the future. It's like a time machine for motion. And what's the most perfect, everyday example of this kind of motion? Simple, an object in free fall. If you ignore air resistance for a moment, any object you drop accelerates toward the ground at a perfectly constant rate. This is exactly what Galileo studied, and it's how he unlocked this entire secret code. Okay, so this is all really fascinating stuff, but what does it actually have to do with us? I mean, why does understanding acceleration and these equations really matter in our day-to-day lives? Well, it turns out they are absolutely critical for one of the most common and most dangerous things we do every single day, driving a car. So let's talk about a really critical idea called stopping distance. When you hit the brakes in your car, you're basically creating a constant negative acceleration. The stopping distance is simply how far your car travels from the moment your foot hits that pedal until you come to a complete stop. And believe me, understanding this can save lives. This right here, this comes directly from those equations of motion we just looked at. And I want you to focus on one word: square. That single word is probably one of the most important words in all of road safety because it has a consequence that is dramatic, powerful, and honestly, a little scary. Just look at this. Let's say you double your speed. You go from 30 to 60 miles per hour. Your intuition, your gut might tell you, okay, my stopping distance will probably double too. But the physics says, nope. Because of that square relationship, when you double your speed, your stopping distance doesn't double, it quadruples. It takes you 4 times the distance to come to a complete stop. And if that isn't sobering enough, here's the final piece of the puzzle. That stopping distance we just talked about, that only starts counting from the moment your foot actually touches the brake pedal. But what about the time it takes for your brain to see a hazard and tell your foot to move in the first place? That's your reaction time. It's that little gap between seeing and doing. It's different for everyone, and it can be affected by being tired, being distracted, anything. And during that entire gap, your car is still flying forward at its full speed. So I'll leave you with this question to think about. The next time you're out on the road, cruising along, feeling that smooth, zero acceleration, think about the language of motion we've just talked about. And think about that hidden distance, the distance your car travels in that silent, invisible gap of time it takes you to simply decide to hit the brakes. Because understanding this language doesn't just help us describe the universe, it helps us navigate our own little part of it a whole lot more safely.